So let's suppose we have some data with observations, 1 through n. We've got n observations on 2 different variables of interest. And these variables of interest could be really whatever we want them to be, but in this case, we're going to give them really generic names. Like those names are going to be x and y. And we could give the specific observations on these different variables, numbers like 3.5 or 4.6 or pi. Okay, but what we're going to do for now is we're just going to sort of chuck in placeholder values for all of these values, these observations on our different variables. So the first observation on x is going to be called x subscript 1, the second observation is going to be called x subscript 2, and so on until we get to the final observation, which is x subscript n. Okay, and we can do the same thing for our variable y subscript 1, followed by y subscript 2, which is paired with x subscript 2, all the way up to y subscript n. Okay, and when we have data like this, when we have for each observation, we've got sort of 2 numbers, there's sort of a unique and a very useful way that we can represent these data, okay? And so just drawing a set of axes over here and putting on the y-axis, no surprises, the variable y, and on the x-axis, the variable x. If we have a particular observation, okay, like observation 1, we can mark out where x1 is on the x-axis, and we can mark out where y1 is on the y-axis, and we can find the point at which these 2 values of x and y meet, and we can put a little dot there, okay? And we call this this dot represents that first observation from the data. We can do this with all of our data points, so x2, x3, x4, x5, and so on, just plotting our data points in this 2-dimensional space here, this 2-dimensional space. Okay, that's plenty. Okay, and so when we do this, we call this a scatter diagram, as you can see, because all our data points are scattered around this 2-dimensional space. This is a really useful technique to use because this allows us to sort of see at a glance what the general relationship between our variables x and y is. And it does seem to see that, low values of x do correspond with low values of y, and high values of x do seem to correspond with high values of y. And so we've been dealing up until this point with sort of answering very specific questions about a certain variable or relationship between 2 variables. And what we're going to be moving into now is this idea of modeling. And very loosely, modeling is where we represent a relationship between 2 variables like x and y with some sort of mathematical equation or mathematical relationship. And the simplest kind of mathematical relationship like that is a linear one, where we say, okay, the relationship between x and y is just some linear line. Okay, and so we can draw, some sort of representation of this model as a linear line on this diagram here, like that. Okay, so this is just a line that's going to be passing through our diagram, passing through all these points. This line is sort of an attempt to capture what we're seeing in the data here, capture this relationship that we're seeing in all these dots here. And you'll notice that this line only really passes through one of these data points, but that's not really a massive concern. I mean, for example, if we tried to draw some sort of line that went through all of these data points, it ended up being a bit of a mess. It wouldn't really tell us much and be very, very arbitrary, very specific. And we're sort of content with this not being perfect. We're content with this sort of being just an approximate representation of reality here, this line. And so just like we had for a particular value of x and y, a little point in space here, if we draw a line from that x value to the point on the line, we can go and find the corresponding y value for that point on the line. We call this one y1 hat. Okay, and we can do this again for another point, such as this point over here. Okay, let's call this x2, then the bottom here, and it's corresponding to the y value, y2. But when we keep drawing this line up until it hits our line, up until it hits our sort of representation of the data as a whole, okay, we're going to get a corresponding predicted value of y given our independent variable x. Okay, and so you'll notice here, this model does not perfectly fit the reality we see in our data. And so whenever we have a particular data point, it's not going to be exactly on the line. And we embrace this. We embrace this specifically by measuring just how wrong our model is, okay? Just how far away our model is from reality here. And so we're going to do that by measuring this distance here between this point on the line and this point in my data, okay? And so we're going to give that a special name. We're going to call that distance an error, okay? And that shouldn't be too hard to remember because it's just how wrong the model is. You know, if it's bigger error, the model is more wrong for this particular data point. And in a specific mathematical sense, we're going to call this error E, and we're going to give it a subscript 2 because this is corresponding to the second data point. And it's going to be equal to my data, y2, minus my predicted value, the point on the line corresponding to that x value, y2 hat. And we can see here, y2 minus y2 hat is going to be some negative number. Okay, and we can compute this error. We can compute this error for any data point we want. We can see here that we've got a bit of data that's particularly close to the line. And we can write, okay, our error is going to be E1. It's going to be equal to Y1, the data, minus Y1 hat, the corresponding point on the line. And the size of this E1 is going to be smaller than the size of this E2. But in particular, whilst E2 was a negative number, since Y2 is less than Y2 with a little hat, this E1 is going to be a positive number, since Y1 is greater than Y1 hat. And so the difference is going to be greater than 0. And so a natural question to ask when you see a diagram like this one is, okay, well, that's all well and good, but why this particular line? You know, why not a line that's a little bit steeper? Why not one that's a little bit higher or a little bit lower? And that's a very good question to ask. And so we've got to have some sort of criteria for which linear line, of all the possible linear lines, and there are quite a lot, is going to fit this data that I'm looking at right now the best. And the way we're going to do that is using these error terms, because we have this intuitive sense in which these errors are bad. You know, the bigger these errors are, the further away from reality, the further away from the data this line or my model is. And so we're going to say, okay, I want a line that minimizes error. Okay, that's a good start, but we've got to be a bit more specific now, because we've got, actually, if we've got n observations, we've got n errors, and some of them are positive and some of them are negative. And so what we're going to try and do is to say, okay, I don't really care if an error is positive or negative, I just care if it's big or small. And so the first thing we're going to do is, rather than focusing on just these errors, we're going to focus on their squares. And so much like when we're calculating the variance for a variable like x or y, and when we're calculating such a variance, we look at the sum of the squares of all the distances between all the data and the mean in our variable. So too here, we're going to look at the distances between all our data and all of the points, the corresponding points on the line. So we're going to look at all the squares of these errors. And so our criteria is going to be, okay, we want to minimize this sum, the sum of all the squares of the errors. So the sum of all the squared errors. Okay. And so given that we set out and saying, okay, find me the line that goes through this data that makes the sum of all these squared errors as small as possible, there's only going to be one line that satisfies that criteria. Okay. And when we get such a line, we're going to call that line the line of best fit. The line of best fit. So called because it fits the data as best as possible. But we've been very specific in what we mean by fitting the data well. We've said, okay, I want to minimize the sum of squared errors. And so we actually give this line a more specific name. We say this is the OLS, line of best fit. And so what do we mean by OLS? We mean, well, this stands for ordinary least squares. Ordinary least squares. Okay? Now we can see here this name has an exact parallel to how we're choosing to define what's a closely fitting line. We want to find the line that minimizes the sum of these squared errors. Okay? And so obviously we're going to call the line of best fit that comes out of that process the ordinary least squares line of best fit. And so that's what this line is. And so if you give me a set of data, I can find, if I've got two variables like this, I can make a scatter graph and I can find the line of best fit, the line that makes the sum of all the squares of these errors as small as possible.